So picture this. You are sitting at the head of a boardroom table, or, maybe you're a policymaker, staring down a massive national budget.
Right.
And every single day, you are just bombarded with these headlines about how AI or quantum computing is going to change the entire fabric of society overnight.
Yeah, the pressure to act on that is just enormous.
Exactly. But when you're the one actually responsible for writing the checks or setting regulations or securing national infrastructure, how do you separate the science fiction from actual sovereign strategy?
That is the big question.
Right. So for today's deep dive, we're getting into Nishant Prabhakar's book, The Sovereign Stack, Building India's Quantum Foundation. And his whole argument is that to build the future, you have to stop looking at the brilliant scientists in the lab and actually start looking at the plumbers, the supply chains, and the underlying architecture of these institutions.
Which I love because, the expectation for decision makers is always this clean, binary leap into the future. Like a switch gets flipped and boom, suddenly we're in the quantum age.
Yeah. Just flying cars and quantum computers everywhere.
Right. But step into the actual world of national infrastructure, and that clean narrative completely falls apart. It's deeply complex, highly constrained, and frankly, just really messy.
Yeah. The book points out that most technology stories are told backwards, right? We flatter the breakthrough moment, but we completely ignore the boring day-to-day reality of the institutions that actually made the breakthrough matter.
Exactly. And that's why quantum computing is not some global race to be won by whoever builds the fastest machine first. It's a foundational layer that has to be built. It's much more like railways in the 19th century or, the electrical grid in the 20th.
I really want to pause on that historical precedent because it frames everything we're going to talk about today. In the 19th century, the literal backbone of a nation was rail.
Right.
If you controlled the tracks, you controlled the economy. In the 20th century, it was power grids. And today, that invisible backbone is compute.
Yeah, compute is everything now.
It's no longer just a tool or a luxury. It is the fundamental substrate for economic growth and national security. And Prabhakar really highlights that compute ecosystems operate on these brutal winner-take-most dynamics.
Yeah, and understanding those mechanics, why compute concentrates power so heavily, is just essential for any institutional leader listening to this. It's basically a series of reinforcing loops.
Okay, break that down for us.
So first is just sheer scale. Massive centralized platforms can take the astronomical fixed costs of hyperscale data centers, all that cooling infrastructure, and amortize it over millions of users.
Which basically freezes out smaller players before they can even get off the ground.
Exactly.
Yeah.
And then you hit software lock-in. Once an entire nation's developers build their critical workflows on a specific proprietary platform, the switching costs become completely prohibitive.
Oh, yeah. Nobody wants to rip out and rewrite millions of lines of code just to change vendors.
Right.
You're essentially held hostage by your own legacy systems at that point.
You are. And then you have to add the concept of data gravity to that equation.
Data gravity.
Yeah, think of data gravity like a planetary mass. So the more users a platform has, the more data it pulls in. That data trains better models, which provides better services, which attracts even more users.
Oh, wow. So the gravitational pull just becomes inescapable.
It does. And finally, you have talent clustering. The absolute best engineers are always going to flock to the most advanced systems. So all these forces guarantee that compute ecosystems naturally centralize into these strategic choke points.
So if a nation or a major institution relies entirely on external platforms, they're basically outsourcing a core capability that just compounds in importance every single year.
Precisely.
And that sets up the stakes perfectly, I think, which introduces this really heavily loaded word we need to talk about: sovereignty.
Yeah, that word carries a lot of baggage.
It really does, because usually when people hear technological sovereignty, they picture this sort of digital isolationism, like closing the borders and trying to manufacture every single microchip and server domestically.
Which is impossible.
Right. But the book entirely redefines sovereignty for the digital age. I like to think of it like a national highway system. You wouldn't let a foreign competitor own all your roads and dictate who gets to drive on them.
No, of course not.
But maintaining sovereign control of that highway system doesn't mean you have to manufacture every single car that drives on it yourself.
That is a great analogy. Sovereignty in this context really just means agency. It's the absolute ability to run your critical workloads without asking for external permission or, fearing some arbitrary shutdown.
Right.
And that requires a modular stack. Just look at India's success with digital public infrastructure or DPI stuff like digital identity and unified payments.
Yeah, those systems are fully interoperable with global standards, right? Like
Right.
an international bank can plug right into them.
Exactly. But they are sovereign by control. India owns the foundational routing layer. No outside entity can just flip a switch and turn off the payment grid.
But building that foundational layer for something as advanced as quantum computing actually requires starting with something much more familiar, which is artificial intelligence. The book really pitches AI as the crucial on-ramp here.
Yeah, AI is the demand engine.
Right.
Because quantum doesn't just arrive one day and replace classical computers. If you build this pristine quantum machine in an isolated academic lab, nobody in the real world is going to know how to use it.
That makes sense.
AI normalizes the whole concept of shared national access to immense compute power. When programs like the India AI mission distribute access to high-performance GPUs across universities, startups, government agencies, they're actively building institutional muscle memory.
Wait, let me make sure I'm following this. Are we talking about like the unglamorous bureaucratic stuff, the
Pretty much.
booking systems and the rules of access?
Exactly those mechanisms.
Yeah.
We're talking about service-level agreements or SLAs.
Yeah.
The binding contracts that guarantee a specific level of uptime so a researcher knows their job will actually finish.
Okay.
We're talking about priority queues, how a government decides whether a weather simulation for an incoming hurricane preempts a university's material science calculation.
Oh, wow. Yeah. Somebody has to make that call.
Right. And secure enclaves. Those highly protected digital vaults where sensitive healthcare or defense data can be processed without ever touching the broader network.
So when an institution builds these governance structures for AI today, they're basically writing the exact operating system they'll need for the quantum era tomorrow.
Exactly. They are training an entire generation of users to think in terms of hybrid, distributed workflows.
Okay, so if we accept that we're building this massive, sovereign, highly governed highway system, we do run into a major conceptual roadblock regarding the actual vehicles we expect to drive on it.
The quantum computers themselves.
Yeah. Because the popular hype cycle tells us that quantum is going to entirely replace classical computing. We're led to believe GPUs and traditional processors will just be obsolete overnight.
And that framing forces decision makers into this deeply flawed choice. Invest everything immediately or risk being permanently left behind.
But that's not the reality, is it?
Not at all. We are currently in the era of NISQ noisy intermediate scale quantum devices. The physical reality of these machines is that qubits, the fundamental units of quantum info, are extraordinarily fragile.
How fragile are we talking?
Hypersensitive to microscopic fluctuations in heat, to the slightest mechanical vibration, even to background cosmic radiation. Every millisecond a qubit exists, it is losing information to its environment.
Oh, wow.
Achieving true error correction, where the machine can actually fix its own mistakes on the fly, requires massive overhead. It is a very long road ahead. So quantum is not a wholesale replacement for classical computing, it's an augmentation.
Okay, before we apply this to national infrastructure, I need to understand what this machine is actually doing differently. If it's just an augmentation, how does it process information in a way that a standard supercomputer just can't?
Well, consider how classical computers solve complex optimization problems. They operate sequentially. So if you need to find the fastest route through a massive maze, a classical computer essentially acts like a mouse.
Okay.
It runs down one path, hits a dead end, backs up, and tries the next. It does this incredibly fast, millions of times a second.
Yeah.
But it's still testing routes one by one.
Right, brute force.
Exactly. But a quantum computer operates on different physical principles, superposition and entanglement.
Yeah.
So instead of sending a mouse into the maze, it floods the entire maze with water.
Oh, that's a great visual.
Right. The water explores all possible paths simultaneously. And through quantum interference, the wrong paths cancel each other out, while the optimal paths amplify each other. It maps the probability of the best routes all at once.
That fundamentally changes how you approach complex logistics.
Yeah.
And Prabhakar argues that quantum's first real-world utility won't be in these pristine academic simulations, but in massive, messy, high-friction systems. Like, Indian Railways is the perfect example from the book. It's this living, breathing organism. Thousands of freight and passenger trains sharing a finite network of tracks designed for a totally different era.
It's incredibly complex.
Right. A delayed freight train in one zone creates this ripple effect that becomes a scheduling nightmare for commuter trains hundreds of kilometers away.
And when classical optimization tools try to solve that, The constraints pile up so high that the solvers have to artificially oversimplify the problem just to run the math.
They flatten the reality. They have to pretend certain variables just don't exist to force a solution.
Exactly. But quantum optimization embraces the complexity. It doesn't promise a perfect, mathematically clean answer. It offers probabilistic exploration,
Okay, meaning what, practically?
meaning it samples from that massive, tangled web of competing constraints, train speeds, platform availability, crew shifts, and it suggests alternative scenarios that a classical brute force approach would just overlook entirely.
So it might say something like, if this specific freight train holds at a siding for exactly 7 minutes, it'll organically resolve 3 passenger train conflicts downstream.
Precisely. And in a system moving millions of people daily, saving 7 minutes here and there compounds into millions of hours and billions of dollars saved.
That's incredible. And the same logic applies to managing shipping ports, right? Coordinating the chaotic dance of container ships, offloading cranes, transport trucks.
Absolutely. Or the national power grid. The moment you introduce massive-scale solar and wind energy, the grid becomes highly volatile.
Ugh.
Operators have to balance unpredictable weather with real-time energy demand.
Or the public distribution network, moving millions of tons of grain to feed citizens while trying to minimize spoilage and routing delays.
Right. Quantum acts as a highly advanced assistant in these environments. It continually explores trade-offs and generates alternative scenarios. It accepts the inherent uncertainty of the real world rather than pretending the variables can be perfectly controlled.
Okay, but I have to play devil's advocate here, especially for the institutional leaders listening.
Go for it.
If these qubits are as incredibly fragile as you just described, and they only offer probabilistic suggestions rather than definitive answers, why should a transport minister or a power grid operator care right now?
That's the billion-dollar question.
Like, if I'm writing the budget, my instinct is to just let the Americans or the Chinese spend billions figuring out the error correction, and I'll just buy the stable hardware from them in 10 years.
I hear that a lot. But waiting 10 years means surrendering the chance to learn how to integrate these tools into tightly regulated workflows.
What do you mean?
Well, suppose a quantum system gives a probabilistic suggestion to a human air traffic controller or a grid operator. How does that human actually verify the suggestion? How do you build operational trust when the machine is suggesting a probability rather than outputting a hard binary decision?
Oh, I see. You can't just buy that kind of institutional trust off a shelf.
No, you cannot import workflow integration from abroad. You have to physically build the ecosystem and learn those lessons in your own context. To learn that integration, you have to build the ground beneath the machine today.
And building that ground is entirely different from throwing up a standard data center. You can't just slide a quantum processor into a server rack next to your corporate email servers and, crank up the AC.
No, not at all. Quantum facilities function much more like advanced particle physics laboratories.
Right.
They require extreme cryogenics, utilizing specialized dilution refrigerators to drop temperatures down to fractions of a degree above absolute zero. That is colder than deep space.
That's wild.
They require intense vibration control. Like a heavy truck driving on a road a mile away can introduce enough seismic noise to ruin a quantum calculation.
A truck a mile away?
Really? Yes.
Yeah.
They demand immaculate, dust-free clean rooms and heavy electromagnetic shielding. It's a completely different real estate game.
And this physical reality forces a major shift in national strategy. The book strongly argues that nations like India should not blindly chase the global race for the most advanced QPU, the actual quantum processing unit itself.
Yeah, the QPU is the chip where the qubits live. And trying to dominate that specific component requires a semiconductor fabrication ecosystem that takes decades and hundreds of billions of dollars to build from scratch.
So instead, the focus shifts to the indispensable supply chain, what actually allows a quantum computer to function.
Right, the picks and shovels.
Exactly. It's the intricate control electronics that translate software commands into physical microwave pulses. It's the highly stable lasers used to trap individual ions, the ultra-high vacuum environments, the metrology equipment for microscopic measurement.
And nations with deep existing expertise in precision engineering from aerospace, defense, telecom sectors, they are perfectly positioned here.
It really makes me think of how you build a domestic aerospace industry. You don't start by trying to manufacture a rival to the Boeing 747 entirely from scratch.
No, you'd fail immediately.
Right. You start by manufacturing the landing gear, the advanced avionics, the environmental sensors. You make yourself the indispensable manufacturer of the nervous system, not the metal shell.
That's a perfect way to put it.
And if you build the precision control electronics, your supply chain becomes crucial no matter which specific qubit physics, whether it's superconducting, trapped ion, or photonics, ultimately wins the hardware race.
You build durable, compounding value, regardless of the underlying physics, but manufacturing the physical components still leaves a massive gap.
Which is?
Well, the average software developer or logistics manager or financial analyst, they are never going to set foot inside a cryogenic physics lab.
Obviously not.
They will access this compute power remotely through the cloud. So the access layer, the digital doorway, matters significantly more for adoption than the machine itself.
If the machine is too difficult to use, it just becomes a very expensive paperweight and it needs a familiar API.
Yeah.
And for the non-technical leaders listening, an API is basically a digital menu. It allows a standard software developer to order a complex quantum calculation using programming languages they already know. They don't need a PhD in quantum mechanics to operate it.
Right. And they also need sandboxes, safe, simulated digital environments where developers can experiment with quantum algorithms without the risk of tying up or, crashing a multi-million-dollar physical machine.
And if an institution intends to run critical financial or defense workloads on these machines, anonymous compute access is a complete non-starter.
Oh, absolutely. You need robust identity frameworks. You must know exactly who submitted a job, verify their cryptographic authority to run it, and maintain a completely traceable, tamper-proof audit log.
So by building this secure, highly governed doorway, you transform a fragile science experiment into an actually deployable, trusted national service.
Yes. And for an investor or a government procurement officer, this should be the light bulb moment. The software layer that manages the identity, the APIs, and the audit logs. That is actually a much safer, more predictable investment right now than the physics experiment happening inside the freezer.
Which brings this entire conversation directly into the boardroom. How do governments and private equity actually pay for this infrastructure, and why is it a priority today?
Well, in the boardroom, the conversation pivots entirely from scientific curiosity to institutional risk. And specifically for the banking and financial services sector, the wedge that forces quantum onto the immediate agenda is post-quantum cryptography.
The harvest now, decrypt later threat.
That's the one. The encryption that currently secures our global financial system, our power grids, our private communications, it all relies on mathematical factoring problems. Classical computers would take millions of years to solve them.
But future, fully error-corrected quantum computers will crack them in hours.
Exactly. And state-sponsored adversaries are actively harvesting encrypted data today. They are siphoning financial records, state secrets, proprietary IP. They cannot read this data right now, but they are storing it in massive server farms, patiently waiting for the day a quantum computer comes online to decrypt it.
So the data basically has a ticking clock attached to it.
It does.
And this temporal asymmetry means that migrating to quantum-safe cryptography is not some distant technical upgrade for a bank's IT department. It's an urgent balance sheet decision for the CEO today. You cannot swap out the cryptographic foundations of a legacy banking system over a weekend.
No, it's a multi-year, highly disruptive transition. And this immediate urgency fundamentally changes how governments and institutions have to approach procurement.
Right.
Historically, public and corporate procurement buys fixed specifications. You write a rigid tender for a server that has X gigabytes of RAM and Y processing speed, and a vendor delivers exactly that box.
But with emerging volatile technologies like quantum, you don't even know the exact specifications yet. The hardware is changing every 6 months.
Exactly. So you have to stop funding specific technologies and start funding problems.
You shift from traditional procurement to outcome-based procurement. You don't buy a server, you buy a verifiable 5% efficiency gain in your logistics routing.
Yes. You reward continuous progress, adaptation, and institutional learning, rather than just strict compliance to a static document written 3 years ago.
And this paradigm shift directly aligns with how sophisticated private equity views the sector. Private equity gets criticized a lot as impatient capital, but what they truly avoid is unpriceable uncertainty.
Right. They have no interest in betting on a speculative science project where the entire return profile depends on one brilliant physicist achieving a miracle. They require predictable, manageable cash flows.
So for the people writing the checks, the mandate is to stop looking for magical unicorns and start building boring, reliable factories. We need capital that understands infrastructure.
Exactly. Private equity belongs in the layers of the stack where the technological uncertainty has already collapsed, not the QPU moonshots. They belong in the physical, specialized facilities that house the machines, backed by 20-year leases from national laboratories.
Ah, I see.
They belong in the compliant software platforms, managing that massive cryptographic migration for the banking sector, in orchestration software, and in rolling up the fragmented, highly specialized service providers who, calibrate the lasers and maintain the vacuum systems.
These are highly regulated, multi-year transitions with embedded annuities. It is about enterprise compounding, not venture-style hypergrowth.
Exactly.
So to bring it all together, the sovereign stack is ultimately a call for disciplined, hype-free ecosystem building. It's a blueprint for leveraging the classical and AI infrastructure we already have, utilizing probabilistic exploration to solve messy, real-world bottlenecks, and capturing the critical component supply chain through precision engineering.
And entirely rewriting how we procure and fund innovation. It provides a deeply pragmatic framework. Technological sovereignty isn't achieved by wrapping a flag around a microchip or cutting yourself off from global innovation. It is achieved by having the absolute agency to integrate, audit, and govern complex systems on your own terms.
You have to transition from being a dependent consumer of black box technology to a co-creator of the foundational infrastructure.
Could not have said it better.
Which leaves us with a critical question for you, the decision maker listening right now. If true technological sovereignty is about having the agency to deeply understand and control the infrastructure your entire operation relies on, what other black box technologies is your institution blindly trusting today? Where have you completely outsourced your understanding of the underlying stack, simply because the mechanism was too complex to bother learning? Because if you don't understand the ground beneath the machine, eventually someone else is going to decide how your systems run. Something to seriously consider the next time a vendor pitches you a miracle in a box.